So thanks for the introduction. I'm Tommaso, and I'm presenting our work, which is Selfrando. So our work is a joint work of TU Darmstadt, Immunant Inc., the University of Padova, and the Tor project. And you may already know something about Selfrando because of the good media coverage that we had, but let's start with the motivation. So I guess you already know what Tor is, but I will do a very short introduction nevertheless. This series of proxies that can be used to prevent a web server from knowing the IP address of a particular user that is visiting it. So if an attacker wants to perform a deauthentication attack, that means that to know who a user is, the attacker can do two different things. It can do an attack on the network, just as we just heard in the previous talk, or it can attack the application on the endpoint, in this case, Tor browser. And for this talk, we will focus on this second attack. It was recently discovered that in 2013, the FBI did an attack like this. They compromised the server and had it send malicious code back to requests coming from the Tor network. The malicious code exploited a vulnerability in the Tor browser on the user's machine and executed malicious code there, and then sent personally identifying information back to the FBI, bypassing the Tor network, so in the clear. This means that you don't have to be the NSA and control the whole internet to be able to anonymize a user. You just need to control a web server. Our work is a defense against this kind of attack, and so let's take a closer look at how an attack like this works. An attacker can use two different types of runtime attacks, and can choose a code injection attack or a code reuse attack. This is a graph of the different blocks on an application. And let's assume one of these has vulnerability. What the attacker can do is inject malicious code in the application memory, and then redirect the vulnerable code to that function, or to that code. And with the widespread deployment of data execution prevention, or DEP, an attack like this is no longer possible. However, there is still the second option, which is a code reuse attack, which starts in a similar way with the attacker using the vulnerability, but the target of this vulnerability is not injected code. It is a part of the legitimate code of the application. And so the application runs legitimate code in a way different from what the programmer intended. A usual way to do this is to stitch together sequences of instructions that are called gadgets. So the defense that has been used against this kind of attacks is randomization. And randomization can be done on a number of different levels of granularity. One can do segment granularity, which is called the ASLR, or address space layout randomization, and which has very good performance, but it is quite easy to bypass since the whole memory of the application is moved by a random offset. So if the attacker is able to determine what this offset is, everything else is easy for him or her. On the other end of the spectrum, one can do block level or even instruction level randomization. However, the security here is very good. However, the performance is not great here. So we chose to find the sweet spot in this spectrum, and the best compromise we found is function level granularity, and this is where Selfrando is. So we already mentioned two of our goals, which are speed and security. Let's look at all of them. So our first goal was to be easy to adopt for the Tor project and also other developers. And then we wanted to be want our defense to be secure, and this means to prevent most real-world attacks. We want it to be very easy for users to run a program that uses our defense. This means just download it and launch it without any system configuration. We want it to be compatible with large and complex C, C++ applications like a browser. And we wanted it to be fast with a target of about 1% overhead. So previous work on this on randomization exists, but compared to previous work, our defense is compiler independent, which means that we use an unmodified compiler and we just use a custom linker wrapper. We have no dependencies to proprietary software, which is obviously a problem if you want to include your defense into open source projects like Tor browser. We don't have a custom loader or modifications to the kernel, which is very good for users because they don't have to change anything on their system. And finally, we don't require any modification to the source code of the application, which is very good for complex programs. Before we look into how our defense works, let's look at the threat model we assume for the rest of the talk. We assume state-of-the-art defenses, which means data execution prevention prevents code injection attacks. And we have address space layout randomization deployed as well. These are both widely deployed defenses. On the other hand, the attacker can use a vulnerability to read and write data. And it can also try to mount a code reuse attack like a return-oriented programming attack, which works as I mentioned earlier. Let's now take a closer look at how our defense works. So normally, the developer just distributes the binary of the application to all users, and every user runs exactly the same application. This means that if the attacker can attack one of them, and the same exploits works for all of them. What we do is also to ship the same binary to say application to everyone, but then it randomizes itself every time the user runs it, which means that from the attacker point of view, these applications look as different applications. And even if the attacker is able to attack one of them, it is not able to attack the other ones because they look different. Let's now take a closer look at the implementation. So, as we mentioned, we have unmodified compiler that reads the source files and produces object files. Usually what happens is that the linker compiles the objects file into one executable. However, we have a custom linker wrapper that does the normal thing, so the linking, but after that, it also includes in the binary the code that actually does the randomization, which we call randolib. And moreover, our code needs to know where the functions are in order to randomize them. And to do this, it analyzes the object file and the executable file and puts this data into the function metadata section of the executable. Now, the developer distributes this binary to the users. And when the user clicks on our program, the first thing that executes is randolib, which reads the function metadata from the binary itself and does the randomization to the code. Then it fixes the references between the different functions in order to make the program actually work after the randomization. And finally, it calls the main function at the new address, and the new randomized address. Let's go to the evaluation section. So first, the security part. We have considered two different attacks, the brute force attack and the information disclosure attack. We focus for the brute force attack to 32-bit systems since ESLR, address space layout randomization, is vulnerable on 32-bit systems since it only provides 9 bits of entropy. Selfrando makes these attacks infeasible because it provides for normal programs at least 22 bits of entropy for each gadget the attacker needs, which is at least 3 usually. So it is significantly more entropy. Regarding the other attack, we focus on an attack where the attacker wants to disclose the address of a particular gadgets in the memory. We analyzed a few recent exploits, and we've seen that all of them use these two very vital gadgets, and these are quite rare gadgets as well. And we analyzed the common vulnerabilities, and we determined that it is not feasible for the attacker to disclose the address of these gadgets in memory. Thus, we conclude that Selfrando is able to defeat real-world attacks. We are conscious that we are still vulnerable to sophisticated academic attacks like just-in-time ROP, which is an academic attack. However, there are more advanced defenses like Redactor to defend against this, but this kind of defenses have dependencies problem and or require dependencies and also have a higher performance overhead than us. So let's look at the performance then. These are numbers for Tor browser. On the left side, you can see graph of the load time of Tor browser, which means the time from which the user clicks on the icon to when he can actually use it for one particular system. And without Selfrando, it is 2 seconds, and with Selfrando, it is 2.4 seconds, so it is a very small overhead. We measure the JavaScript overhead as well, using various standard benchmarks, and the geometric mean is about 2% overhead. Moreover, we also tested with the industry standard spec CPU 2006 benchmark suite in order to have an idea of how our defense deals with more general programs. And we can see that geometric mean is well below 1% for both CLang and GCC, which are the 2 compilers we tested. And the only outlier, the elephant in the room, is Xalang. And we analyzed why it has such high overhead, and we determined that it relies heavily on function locality, which means that certain functions need to be near to each other to have good performance. However, the other benchmarks do not have such a high overhead, and this means that relying on function locality this much is not usual. Finally, let's take a look at Tor browser specifically. As we said, the Selfrando provides a single binary that can be distributed to all users. And Tor browser, as you might know, use reproducible build system, which is Gitian, and this means that the same binary can be compiled by everyone, given the sources. This is to make anyone able to verify that the binary is not compromised. And for this reason, having a load time randomization solution is very good for a fit for them. Another hard requirement on Tor's part was to be compatible with Address Sanitizer, which is a tool used to detect memory bugs in the beta releases of Tor browser. So we are proud to say that our work, Selfrando, is already included in the hardened nightly build of Tor browser. It has been for a couple of months, and they plan to include it in the stable release for Linux next year. So, to conclude, we have presented the first practical mitigation against runtime exploits for Tor browser, but it's still generally applicable to other programs as well. Selfrando significantly raises the bar against runtime exploits. It is compiler independent, self-contained, and it is easy to adopt for both users and developers, and it has real-world impact since it is in the process of being deployed by Tor browser. And finally, as future work, I mentioned that we could add some practical mitigation against more advanced attacks, like what we mentioned, maybe based on Redactor. So thank you for your attention, and I would welcome some questions.